can start with that. And the idea is to kind of focus on how can you do a better design in terms of like just when you're interviewing. Like that is the idea. So maybe there might be times where there are specific questions that you have come across from an interviewer, and how do you answer that? We can also discuss that maybe in the context of this question. Right? That will be better. Let's start. What I'll do is I'll pretty much like use this whiteboard. Like this is a blackboard that I'll end up using, and you can see my screen, right? And this document is already like shared with you. So this document has the like part of the lecture that I'll go through. And in no way it's complete, in no way it's but it's a specific problem that I tend to ask like system design in system design interviews, and I'll give you my perspective, what I'm expecting from people, right? And feel free to stop me and like talk about any questions you have, right? So that is important, because otherwise like it becomes just a monologue and you'll very quickly, I'm pretty sure, get bored of it, right? I'll kind of begin, right, with what I kind of wanted to cover. Right, so let me just set up one more thing. Uh, oh, okay. I'm just doing it for the first time, so there might be a few glitches. Just bear with me. ठीक है. Just have the setup. Let's start like with what the problem statement is, right? So the problem statement that in my mind, and then what is the problem statement that I tend to ask is that you are given a. Actually, I should have just set it to auto admit. I'm just being asked to admit people. Right. So the problem statement is like, let's first go through what the functional requirements of the problem statement are. So what you want to design is you want to design a system like a search engine, which can pretty much do prefix and exact matches, right? The idea is that, let's say, what's an application of it, right? So let's say you are designing a Google search engine, right? And you have like a list of cities, right? So the list of cities could be, it could be like Delhi, and you could have Dubai in it, right? You could have San Francisco, right? You could have London. And what the user is kind of looking for is, when the user types in the word, the letter D, then they should get completions like Delhi, and they should get Dubai, right? Which is pretty basic, right? If they type in the word London, they should just get one completion, one match, which is London, right? And this is like the most basic thing that you end up doing with any search engine, right? So have a prefix and exact matches, right? So I've limited the scope of the problem, not to make it like more complex, right? But the complexity of like the problem basically occurs in the non-functional part, right? So what are the non-functional requirements? Right. So the non-functional requirements of this problem is that you need to design a system which has very low latency, right? So the latency should be that it should be able to answer the questions that you're asking. When you're typing in, it should be able to answer the questions in less than 10 milliseconds, which is usually very, very fast, right? The system should be scalable, right? So the way I kind of frame this question is that, let's say you have like 100 billion strings, right? So pretty much like all strings in English alphabet, like you're just indexing everything, like maybe on Wikipedia. So there may be 100 billion unique strings, and how do you index that, right? So that's where like a lot of complexity kicks in, right? And then the others are, you need to make the system highly available, right? So pretty much you're shooting for maybe 6 nines of availability, right? So pretty much like system should never go down, right? That is the thing that you're trying to kind of try it for. And the system should be, in the sense, it has to be customizable, right? So that's a slightly different question, and we might end up not covering that. But the idea is that you should be able to index any kind of semantic data, right? So it may not be such cities, it may be any string, it may be a small string, it may be a large string. Like there should be no like limitations on what you can index, right, in terms of data, right? And then on the throughput side, the way I kind of put this question is that I lax the throughput. So I say it's okay that if you can get to say 1,000 requests per second, right? Typically, like I was just looking up what the data for Google is, and Google's data is like it has around 40,000 requests per second, right? So it need not be as fast as that, like as highly, like the throughput need not be as high as that, but like 1,000 requests per second is also pretty significant, right? So pretty much as you start to see this, what I'm focusing on is high scale and be it very fast, be it really available, but like throughput and like other constraints are slightly kind of removed, right? And one of the things that I usually kind of provide is in the problem is that you can assume that you have infinite resources, right? To start off with, right? And as you kind of go into the problem, you can constrain the resources. But like in an interview, like maybe it's an 1 hour long interview, you just can't like uh, uh, constrain every resource, because then like discussion takes like can take many hours, right? So infinite resources basically means you have infinite disk, right, space, which is now pretty common. Like on S3, you have infinite disk available and infinite memory, right? So you can use as many number of servers as possible. It should be okay, right? So this is like the list of non-functional requirements, right? And feel free to stop me and ask questions, because like if you don't ask questions, like you will not also enjoy the whole process, right? So that's being said. So idea is design a prefix autocomplete engine, a exact match engine. Has to be very fast, very scalable, and available. Throughput and other constraints are slightly lessened, right? So how do you kind of go about? Uh, uh,
Ravi,
Go ahead, go ahead.
yeah, I have a quick question, not related, but
Uh,
will you be sharing this recording after this session?
I'll share it on the email. Yeah,
Thanks a lot.
I'm recording. Okay, okay. So the first thing that I usually do with like interviews is that like you need to be able to bound the system, right? So what is the like system boundaries that you have uh, come up with, right, based on the problem, right? Because every problem has a different set of system boundaries, and to be able to do that, to be able to get the intuition of what data structures you use, whether the and we'll walk through each of those questions. Like there are certain numbers that you should know, right? And this is something that I found like a lot of people do struggle with. Like when I take interviews, then I usually ask them, right, let's say what is the access latency for like L1 cache, right? The cache that sits in your hardware in the uh, the cache that sits in your hardware. What is the access latency to that? Right. So usually that is like in nanoseconds, right? Just sits behind, like before the memory, right? And what is the access to the latency to main memory? So it generally tends to be like hundreds of nanoseconds. When you come to the solid, like when you come to the hard disks, right, there is solid state drive, which is usually in hundreds of microseconds. Then there is access to disk, which is usually in tens of milliseconds, right? Because the disk has the rotating like structure, and then you kind of move the head around, which is like the most old way of accessing data, right? And then you also need to know, like in general, network latencies, how much they are. So a round trip within a data center may take microseconds, like hundreds of microseconds, but on wide area network, it may take like probably some milliseconds. It will probably end up taking like hundreds of milliseconds. Yeah, that's very much what it would be. And then in terms of memory, assume like a typical web server that you get tends to have like 250 gigs of memory, right? You could have bigger web servers as well. Now with like AWS, you have daily big web servers. But back then, like you usually used to have out of the shelf, assume that 256 is a good number to go with, right? So some numbers basically help you. And like these, when you kind of discuss like a lot of these problems in system design, you will never get to an accurate view, right? Because different systems have very different properties. But what the interviewer is looking for, and what in general, when you're building a system, what the team is looking for is, do you have a mental model, right? Do you know exactly that this is the model that you are using, right? These are the numbers you're using. This is the system that will come out of using those numbers. And then when you change the numbers, you can change the constraints, right? You can change what the output looks like, right? So there is this very good like GitHub post. I think this is probably shared by Jeff Dean at Google, and they have like tens of numbers, and you can go through it. Gives you a little bit idea. And what I've seen like a lot of people struggle with is sometimes they confuse access to memory in microseconds or milliseconds and it's from nanoseconds, or they do it reverse and they think that access to disk is not in milliseconds but is in microseconds, right? And what that tends to happen is that you just make very major architectural mistakes, and then like the interview just like you can't really accept that person because that person is not doesn't have very good like control over the metrics, right? This understand like basics of system design, right? So this is the first thing that I usually tend to ask people to see how like ki unki jo depth of understanding, where does it kind of start to crumble, right? So that's one. And then the second is in terms of boundaries, like as I said, we basically said like 100 billion strings, right? So what is 100, like why this number, right? So 100 billion strings is pretty much, you can assume that each string has maybe 100 bytes, right? So 100 bytes, 100 billion strings comes out to be 1 terabyte of memory, right? Uh, and I specifically chose this number because I wanted to ensure that like the memory doesn't fit in one server, because then it's not a distributed system and it becomes a very easy problem, right? So 1 terabyte of memory, and you can assume that a server has 256 gigabytes of memory. So thereby you need at least 4 web servers, right? Let me just check actually if I did my calculations correct. 100 billion strings comes out to be 10 terabytes, sorry. So then it becomes 40 web servers, right? So it's a massive scale system that you basically need, right? And at 1,000 requests per second, it basically comes out to be that a web server can handle, you can assume 250 requests per second, which is queries per second. So you can assume that you need at least 4 web servers to handle any kind of workload, right? So this pretty much is not the bottleneck. The bottleneck is this, right? And the way this problem is framed, I wanted to ensure that memory remains the bottleneck. And you can only understand that because it's hidden in the problem, right? You can only understand when you have control over these numbers and you can basically do this math calculation, right? And usually what I see is that only 10% of the engineers or less than that are able to do these calculations upfront, because sometimes like we are just too worried कि ये numbers सही होंगे कि नहीं, right? That's like, are these numbers correct or not? And we just don't have this mindset of like doing the math when you're designing systems, right? So uh, if I see someone doing this math, I just know that that person is a good engineer, no matter the math is right or wrong. If the math is wrong, then I basically help them adjust the math, and if it is correct, then of course like they're really good, right? So just like that mindset, like keep that in mind. And what the system boundary gives you is it gives you understanding of, okay, we probably need 40 web servers, right? So it will be a massive scale parallel system. Throughput is not a major problem, right? And latency is another thing, right? So let's also think about what the latency is. So we said that the requirement was the latency has to be 10 milliseconds, right? Which basically means that mostly solid state drive or a disk is out of question, right? Because the disk is milliseconds and the solid state drive is microseconds. Um, Sorry, not milliseconds. Sorry, this is seconds. Right, and milliseconds is millimicro and seconds, right? So, like if you just do these 3 calculations, you will know that what the interview is looking for, right, in terms of the question. And it's important to like build this boundary upfront, right? So have like if you have any questions, feel free to stop, right? So that would be good. Um, and
So
just
Ravi,
call
I
out.
have a question
Yeah,
here. This
go
40
ahead, go
web
ahead.
servers, right? We picked. This is for storage or for processing? This
This is for
40 web.
storage. This is like I'll come to how why we picked this. This is for basically storing the index in memory.
Okay.
And there are alternate designs. So we'll go through. You can reduce this as well. You need not store everything in memory, right? But the way the problem is kind of like, assume if you had to store a terabyte or 10 terabytes of data and you had 256 gigabyte per server, and this is in memory. I'm just assuming it in memory. Then you need 40 web servers. The alternate design could be that you can also do some
So
80/20, right? So
I'm confused here with the web server. So web server means
hmm,
like Tomcat or those, or just VM we are talking about, some machine. This web server
so
means.
this is you can imagine it a machine, right? So you have
Okay.
a machine that has 1 terabyte of hard disk and 256 gigabyte of
Okay.
memory. So
Got it.
just assuming those configs, right?
Thank you.
And there are variations in configs. Like if you go to AWS, like there are 15, 20 configs of like VMs which are available, which represent basically a machine. Right?
Yeah, Ravi, this Vivek this side.
Huh.
You have the second point, right, where you've said that the requirement is 1,000 requests per second, and we have assumed that we are serving 250 requests per second, right? How did we come to this assumption, right? Because for example, if our latency is 10 ms, right? So one request
Hmm.
is actually taking 1 ms to serve. So wouldn't this request be little less or something? Or should we first decide number of requests that we can serve per server, and then we can extrapolate to that number of servers, or how is it?
Huh. Right, right. So the latency is, as I understand, like the latency is uh, like why does 10 so we can one way to ask the question is why 10 millisecond as a latency, right? And then we can ask
Mhm.
how do we get to the 250 requests per second, right? So these are constraints of the system, right? So when you are going to Google and you are searching, if the search results take 100 milliseconds, right? If the
Mhm.
search results take more time to process, then you will start to see a lag, because human mind is such that we don't see a lag. We think it's instantaneous if it's within like 5 milliseconds or 10 milliseconds. This is like scientifically driven numbers. And so as a system designer, what I've like, let's imagine you have a product manager, right? The product manager said, if it comes within 10 milliseconds, we are good. But if you take 100 milliseconds, then the system will, like the user will start to think that, oh, the system is running slow, or like query results. So that is where this 10 millisecond number comes from, right?
Mhm.
It's just like somebody has asked you to like do the processing within 10 milliseconds. And the 250 requests per second number is pretty much like you can like pretty much like run 250 threads on a server, and after that, like it'll basically saturate, because the reason is that like you just have a limited amount of CPU, and then like if you try to do 1,000 requests per second, like they will basically queue up, right? So that's my understanding how like these numbers kind of come up.
Okay, okay. So let's say number of requests being processed per second is not the function of latency.
Hmm. At least for this, it like we have framed it in a way that it is not. We can do probably a
Okay.
little more map to understand if there is interdependence, but I had assumed it to be independent and said that 10 milliseconds, somebody has asked you to build a system which is 10 milliseconds, and they
Mhm,
have
mhm.
asked you like not to worry about throughput.
Okay.
अगर वो throughput के बारे में भी आपको बोलेंगे तो then it becomes more complex, and I think like in an interview
Understood.
like it will be hard to solve. थोड़ा सा hard हो
Sure,
जाएगा.
sure.
But it's a good question. I'll probably do the math and get back.
Okay, thank you.
Yeah. I mean, this system is also not going to be perfect, right? You can pick a lot of problems. Right? So assume that, right? Keep your mind open. Right? Assume that. So let's try to design it, right? So first thing usually kind of we do is I kind of discuss what is the data structure that you want to keep, right? So there are two approaches. You can go up, bottom up, and you can go top down. Just we have done so, but like bottom up, we can start, right? So in terms of just like the data structure, there are three approaches to building this structures search, right? So one is inverted index, right? And like some of you might know, some of you might not, but we right. So I'll quickly go through the design of it, and then um, uh, like there's binary tree, right, and then there is trie, right. So like typically these three data structures are heavily used, and I try to ask like people that which one do you use and why would you use that, right? So inverted index is pretty much like what a document search is like, where you basically have a bunch of documents, and what you do is that from each of the documents, the document will consist of a bunch of words, right? So what they do is that in each of the word becomes a key in an index, and then there is a postings list, right? So basically, it tells you that in document D1 you have position P1 for W1, right? In document D3 position P3 for W1, and then this gets built. And whenever you do a lookup on a word, you basically you can pull out these documents, right? And you can read about inverted index, how do they work, but the idea is very simple. You basically build a hash table of words, but the values are the document and positions, right? So you basically pull out these documents based on this, right? So that's one. And I'll first like discuss these data structures and then pros and cons as to why we want to use one, right? One of the three, right? A binary tree is pretty simple, right? So in the binary tree, you usually have a node, and then the node has two children, right? And there's the left child, there's a right child, right? And so like usually like you would have say uh, let's say there's number 5, you would have uh, 4 and then 7, like so this is like you can design it like this for general, but you can also design it for strings where you could have like a string ABC and then all the strings smaller than that on the left side, so string larger than that on the right side, and you can order lexicographically, right? And then the third data structure is your trie, right? So the trie data structure is, I think I probably put it already out somewhere before I was right. So the trie data structure is something like this, where you have a bunch of non-leaf and leaf nodes, right? And the idea is that it's a extension. You can imagine it as an extension of a tree, right? And basically each node in a tree, instead of having 2 children, it can have a maximum of 26 children, or a k, which is k is a number, right? And pretty much each letter in it has each like node with it, each node has like 26 children, and each children will be indexed by a character, right? So let's say if you had to index, like for example, Delhi, then what you will end up doing is that you would have D, right? And with D, you would basically have a child, uh, uh, and the child has a child which is of E, and then you have a child for L, and so then you basically reach to Delhi, right? So, and I am pretty sure most of you would have seen try, but this is a good revision. So these tend to be the 3 data structures that we could end up using. And the tricky part is how do you kind of analyze which one to go for, right? So typically the way I kind of go about is that in an inverted index, exact match lookups are good, right? But how do you do prefix? So prefix becomes hard because then you probably have to store prefixes for all possible strings, right? Which is a very, very inefficient way of doing it, right? In a binary tree, the trouble is that even if you store a binary tree, because the limitation is that you just have 2 children, you might end up going to like the design would not be very, very efficient, because you might end up having to design it in a way where that like the lookups may be very, very slow, because you just have a lot of structure like data in the tree, and the tree depth can be really high, right? So I think like binary tree doesn't even fit well with a prefix match system. The best system that fits in is the trie, right? And the reason for that is that trie basically stores keys as prefixes, right? So it's very well attuned to a prefix design structure. For an exact match, I think an inverted index. Sorry, if you have questions, just like feel free to stop. I think otherwise I might miss. Uh, or what I can do is I can come back as well. Yeah, I think I've
We
missed
are
some
putting
questions.
on the chat, Ravi.
Huh, huh. I do see them now.
Yeah.
Correct. So binary search tree is an in-memory data structure, so you might not be able to persist it. Right, that is true. What you can do is you can serialize and deserialize. So I'm not like right now not even worried about persisting. What I'm basically saying is that in memory, what is the data structure you use? There are alternative schemes for persistence, right? That you can do. Or what you can also do is you can basically convert it into a different data structure on disk, keep hotkeys in memory. So there are alternate approaches. So not going right now there. Right. Then let me
So,
actually.
Ravi, a
Ah,
question to you.
right.
So, if in a system design interview, right, even like tree has negative impact. If your data is not normally distributed, then you might end up having problems, right? So, should we mention those things as well? Like this is the potential problem we can have with tree, or should we like completely ignore and wait for the interviewer to ask those?
That's right, right, right. So typically, I tend to give more weightage to if the like the interviewee, which is you as Samir, if you are driving it, and if you want to discuss the pros and cons, right, would like that is good. Usually that is really good sign that you're basically discussing all the pros and cons of the data structure choices, because then I understand that you are basically thinking through the problems, right, uh, statements, right. So that is usually a good sign. That's how I kind of go about it.
Okay.
But yeah, but different like interviewers can be very different. Like some of them may not be like very they might just be looking at the final result. So then that's like not a
Okay.
good interview. But
Thanks.
you could just this. Your question is, Chandan, is that answered or no? Uh, because yeah, you definitely like, BST is in memory data structure. You can't really persist it on disk, but there are different ways you can do on disk, and we can discuss that as well.
But like you said now, for serializing and deserializing it,
Hmm.
anyways, the tree is going to be humongous, right? We can't serialize and deserialize, so that won't help. That's
So right, so there are different ways to do it, right? So one way is let's think from first principles, right? So one way is that you have uh, memory in place, right? And then you have something on disk, and you have a tree in memory, and you can write a serializer and deserializer, right? So that's approach one, right? And of course, like you're right that like serializing and deserializing the in-memory data structures to disk will be very humongous, right? It will also have other problems, right? If you don't, it's very complex to write like memory representations on disk for sure, right? Because just like memory has like pointers and like that can be really problematic. So it's a complex thing to do, right? The alternative is that you basically have same memory, you have an in-memory representation which is right, and maybe this is 20% of the keys, right? Hope you guys can see it. And then what you do is on disk you can keep an alternate data structure, right? Which is you can keep so typically how do databases, and I'm also thinking on the fly, right? Don't have a really good answer, but typically what they do is they have let's say this is the hotkeys that usually are looked up, and then you have an index in memory which basically points to keys on the disk, right? And this may be just like files, right? So you can basically store this as a list of files, and you can basically have a B tree, right? Something like that. And these are like very like this is 80% of data which is cold. Usually access don't go to this, right? So that's like another way like to do it. And maybe you
But
have a better way
Ravi,
to do it.
Ravi, since anyway this is a distributed computing, so can't we shard the B tree and save different segments in different different web servers? Like that would
So
solve the problem, right? Because then you don't have a humongous memory for each server.
correct. So that's the final design we'll kind of get to. But
Oh,
like
sorry.
I was just trying to answer that. Let's say if you had to keep it in one server, right, which is basically vertical scaling instead of doing horizontal, then how do you do it, right? So this is one approach. But I wouldn't for this like set of constraints in this problem, I wouldn't even suggest like putting it on disk. And the reason is that why do you want to put it on disk is that if you put it on disk, then your access latencies, as we discussed, could go into like order of seconds, right? Because like the disk head could move and the tail latencies can be really low, right? So, like can be really high, right? So that thereby, like if you want 10 millisecond access, then you really don't want any touch on the disk, on the critical path, right? Uh, so let's. There was one more question. I just wanted to ensure that I am able to answer that. I'm actually losing track of the can't again. Sorry. Numbers. What's this? It's different. This is so. Sorry. You go ahead. I mean, feel free to. There was this question that was asked by Rohan as well, right? If this is modeled as a web application, then what data structures need to be on front and back end? System boundaries will be because on server side. What data structures need to be on? I see. On front end and back end. I see. So in terms of front end and back, so front end is right. So here, like for this problem, what we are basically discussing is how your back end has to be designed, right? And we can also discuss like what you need to keep on front end, but front end, like I'm assuming it's talking about like just what things should be on the front end JavaScript part, right? Which is different, right? I mean, here we're just talking about how like the backend system should be, and like there should be a data layer, there should be like a distributed like set of servers, right? And then you can process it. That's what I'm kind of referring to. If you can clarify the question, I can try to answer it. That's it.
So yeah, Ravi, break this side. So as we're starting the design, right? Should we not start with a simpler design, which is, let's say, less scalable but simple one? Let's say take a huge server where you store all the data, right? Take one database where you put all the data, and then maybe extrapolate from that. Or rather than that, or should we directly jump into distributed system and complex design, right? So what's the right way about going about it?
So typically, you're right. Typically, the right way is to go about using the first principles approach, which is like you basically start with the simplest design. So what is the simplest design? The simplest design here would be you have a single web server, right? And you have some data in memory. And maybe what you say is that within that simple design, we can only index like 256 gigabyte of data, which is also fine. And then the in-memory data structure could be a try, right? If you want a larger uh, amount of data, then you keep some of it on in a database, and then some of it is in memory, right? So that's how you could start off, and you can then go to like you can then say, how do we scale it to 1 terabyte of memory, right? So then the way you do it is you basically discuss vertical scaling or horizontal scaling, and in horizontal scaling you basically do a distributed system. If you already are very familiar and like have a maybe this got a little complex too soon, that I understand. But if you already are like comfortable with it, then you can directly jump. Right. So, for example, I had like one interview with Google, and they had asked the same question. So I directly jumped to the design that I knew, which is the most like efficient one, and kind of went to that. But like for every problem, you might not even know, right? आपको पता भी नहीं होगा कि how does that. So what you're doing is with the interviewer, you're going more towards more and more complex design. Agreed. I also agree with that.
Sure. Thank you. So it's mostly that we need to maybe read into what interview is expecting, and then from that we can pick it up and solve the problem.
Correct. I usually tend to do that. Like in the sense, I ask them a little bit pointed questions as to within this interview question, what is it that you are trying to get to? But you don't directly ask, but you try to get to a sense, right? So if you understand like the way this I'm trying to drive this question is towards a distributed system which is in memory, right? That's what I'm trying to look for, and I keep nudging the interview towards that and see if they can get to that place. So you have to ask
Sure.
some questions. Right. Because like this, like if you imagine like this system would probably take like months to design. So how can you design it in an hour, right? It's not even possible.
Yeah.
Right.
Yeah.
So
Yeah.
okay. So let's actually I might run out of time. So what I'll do is I'll quickly get to the design part of it, right? So the next part of it, so we kind of said that let's use try, which is in memory. We also said that like you can use persisted structures, like data structure persisted on disk, but the trouble is that disk access tends to be slow, and that question requires you to make a system fast, right? So let's go with try, which is in memory. How do you solve for the next part, right? So the next part is um, you have to ensure that like the system can scale, right? Uh, so in terms like, and you guys already touched upon it, there are usually two ways to scale a system. So there's vertical scaling, right? Which is what you do is that you start with a simple server, which is like maybe 256 gigabyte, and then you kind of go to a 512 gigabyte server, right? And then you kind of go to 1,000 1024, 1 TB server, and so on and so forth. And like the amount of memory just keeps increasing, right? And the alternate design tends to be that you kind of go for horizontal scaling, right? And in horizontal scaling, what you do is that you basically deploy multiple servers, right? And each of them maybe 256 gigabytes, right? And either of those approaches can work. The trouble tends to be with vertical scaling, that after a point in time, very large servers like a terabyte of a server with a terabyte memory becomes really expensive. So usually you don't see the amount, like general the servers tend to have a limit on the number of memory, and that has to do with design of how web servers are. They just can't afford a certain number of memory DIMMs, and so you just can't have like 10 TB server will be very expensive, right? And there are many problems for that. So the way the world has approached this is that they basically kind of have many web servers which are kind of distributed in nature, and you have very simple machines which are distributed. Like you basically have 40 of these, right? So that's the idea, right? And the reason for that is pretty much that that like it's very cheap, right? It's very cheap to have these 256 gigabyte servers, right? So how do you do horizontal scaling, right? And here, like, you just get tested on some very basics of distributed computing, right? So first thing that you should know is that you have to basically shard data, right? So what does that mean, right? So basically sharding, what sharding tends to do is that it will basically take, let's say, the universe of all the strings, right? So maybe there is a and up to z, right? And it will basically break. What you do is you basically break the data into, maybe if it's you may 40 ways, right? And what you do is that on each shard, right? So each shard is a subset of the data. And so on web server 1, you will have shard 1. On web server 2, you will have shard 2. On web server 3, you will have shard 3, and so on and so forth, right? And you will basically use some sharding scheme, right? And I'll go through what like are the pros and cons of different sharding schemes, and you can do it in very different ways. But the idea is that typically you would break the data into smaller chunks, and each web server will have these small chunks, right? So maybe each of this is 256 gig, right? And this is a very simplified model, like in the sense that it may not be the most accurate one, but like it's very good as a representative model, right? So what you've done is you break in the universe of strings into 40 different ways, and you're trying to do it, right? Now I usually tend to ask, like, if a particular sharding scheme, like which sharding scheme would you want to use, right? Because there can be many different sharding schemes, right? So a simpler sharding scheme can be that you alphabetically just sort, right? So just go ahead, ask question. I mean, don't like say the answers. You can ask. Yeah, go ahead.
Sorry, it was a by mistake. Sorry.
Okay, okay. No worries, no worries. Okay. So so you can alphabetically shard. You can basically do a random hash as well, right? And then you can basically do the consistent hash, right? And some of the terms you might have to kind of like go back and like revisit and learn, and that could be the case, because like I mean in 1.5 hours very hard to cover all of these things. But alphabetically sharding is very simple. You can say if there are two, let's say if there are 26 web servers, right? What you do is you put all the A's in one, B, all the strings start with A on one, all the strings that start with like B on the second, all the strings that start with Z on the last, right? You can imagine something like that. Very simple. You can divide the data like that, right? The, the disadvantage of doing that is that if you think in English, a lot of words start with like R, for example, S, and like A, right? And there are few letters. And so what will happen is that the number of strings may get, like you might end up having a what is called a skew, right? So some of the servers may have a lot of strings, some of the servers may have less strings. So that's one problem. And the other is the problem of hotkeys, right? So what will happen is if you're storing cities, then like cities that start with S, so San Francisco, or Singapore, right, or like citizen countries, like they will have a lot of hits. So what will happen is those web servers will start to like basically see a lot of requests, and they will start to become slow, right? So the problem of skew with alphabetic sorting definitely remains, and usually like a lot of people do suggest alphabetic sharding, right? But then I do ask them, if you're going with this, what is the pros and what is the cons, right? So the pro is that it's easy to distribute data like this, but the con is that you can have skew, right? And some web servers will become hot, and some web servers will become cold, right? So that's one, right? And then like the other alternate schemes is you randomly hash, right? So what you do is you basically say a string, and then you basically what you do is you basically take a mod by the number of web servers, right? So string can be represented as an integer, that you can figure out a hash, and then you take a mod, right, with the number of web servers, uh, right? And if you don't like agree with some point, like do call out. Like I mean, nothing is perfect in this, right? You have to assume that. ठीक है कि सब कुछ correct नहीं है, there might be mistakes, so just kind of feel
Yeah,
free to
like
huh, go ahead.
Ravi, putting is fine when we are inserting data, it's fine. But how will we be retrieving it? Like if it's a random hash, retrieval will be difficult, isn't it? Like how will we do that?
Retrieval will be different. Yeah. So in a random hash, retrieval gets a little tricky. If you're doing exact matches, then it's a little easier, because what you can do in an exact match is that um, because you already know a hash, so you have already basically mapped it into a space that you already know. Like for example, let's say कि आपने let's say you have taken Dubai as a string, and you know that Dubai will map to always web server 2. So when you're looking up, you also can look up just web server 2. So then the exact matches के लिए it's easy, but prefix के लिए it might be tricky, because uh, if your hash is not prefix preserving, which means that the hash of dub can go into a different web server, then you pretty much have to look into all the web servers, right? So the lookup part in hashing, which is random, can be inefficient. That's true, right? And एक system के, like in the design of a system, you will have trade-offs. Like as an engineer, like if you're looking at 5 dimensions, then not all dimensions will be perfect. So if you're trying to optimize for memory, then there might be few things that might, like you might have to overuse CPU. That can happen. But you are right in that case that for lookup, hashing which is random is not good. Hashing which is alphabetical is good, because you just know key if it's A, then like all prefixes for A will be web server 1. Right. So you're correct. Yeah. So yeah, so with random hashing, the idea is that you have the string and you match, like you just take a mod, and the mod will basically give you a web server which falls in between the range, right? So maybe the number of web servers is maybe 40, so it will just give you a number between 0 to 39, right? Those value web server mein the index, the string will go. The trouble with random hashing tends to be that in the like actual world is very chaotic, right? We all know that, right? So web servers will go down all the time, right? And the reason why you have chosen a 256 gig machine, like if you go and read original, like some of the works that Google did, they basically used machines which were typical off the shelf web servers, right? So they can go down anytime, memory can corrupt, like this can go down, किसी ने power off कर दिया, like all those things happen. So what the trouble is that if a machine goes down, then what you have to do is you have to rehash everything, right? And you understand that, right? Because the number of web servers in this formula, right? This is basically kind of changing, and once that changes, you have to rehash everything. So imagine like a workload that is running and people are querying, and in the background you're also rehashing everything. You might have to go down, like system has to go down, and then it not doesn't meet availability constraints, right? So random hashing has that problem, right? And so one of the most advanced techniques that is used, and this in itself will take one lecture to understand how this works, which is consistent hash, right? I'll give you a little bit of intuition of what consistent hashing is, but you're interested, you should definitely go and read, and maybe like can do one lecture on it. But the idea with consistent hashing is that you basically assume that your
Ravi,
if you have special,
yeah,
go
Ravi,
ahead.
in the random hashing also you said ki one instance can go down, right? But if we have the replica there, then that issue might not even come up, right? Let's say you have 3 replicas running in parallel. So even if one instance go down, the other one will take the place there. So
You're right.
using that, we
That
can
is true.
sure key we have 40 servers always
Huh.
up and running.
Yes, that is true. So you can always say that, and I haven't talked about availability. So availability may that replication wala thing comes in, which is that
Okay.
in every web server, you can have a part of the web server has strings which are allocated to it, and the second part of it is basically a replica of some other web server, right? So what is a good way to represent it, right? So let's say ki, so let's say ki web server B, on web server B, you basically have replica of web server A, and on web server A, you have replica of web server B. And thereby what can happen is that when your B goes down, right, then you can just search on A, which is the replica. And when your A goes down, you can search on B, which is a common like mm, uh, concept in distributed system design, that you have a replication, and typically you have a replication of 3. So you have one primary replica and then 2 secondary replicas. The only trouble there is that if and you anyways have to do it, you can't avoid it, but the disadvantage of doing usually replicas tends to be that you will use double the memory because each string will have to be in 2 places. So that's one. And the other is that if B goes down, then A will have to use a lot more workload. But you can't avoid it. I think that's a good suggestion. And in availability, that's how you solve for availability. Sorry. Right. And also let's discuss what consistent hashing is, so that at least you know what consistent hashing is, and then if you go deeper into it, you will understand it better, right? So in consistent hashing, what tends to happen is that instead of hashing to a bucket, like a web server, you can imagine it as a bucket. What you do is you basically hash to a range, right? So let's say this is web server 1, this is web server 2, 3, this is web server n. What you do is you basically hash to this range, right? So let's say there is a string called Dubai. So maybe Dubai falls in this range, right? There is Singapore, then maybe Singapore falls in this range. So what happens is that when you assume that if Dubai falls in this range, which is 2 to 3, you move all the strings in 2 to 3 to the web server 3. That is the core intuition. And let's just assume that the core intuition holds, right? So what you do in this is that if let's say a web server goes down, right? So let's say W3 goes down. So what you do is instead of you just move all the strings that map to W3 to W4. And it's like an advanced data structure, so you need not know it, but it's good to kind of learn about it, right? So in a sense, this is also randomly hashing. It's basically putting Dubai in a random range, Singapore in a random range. But the advantage that this data structure has is that if one web server goes down, you don't have to rehash everything, right? So you will just rehash the strings that fall in the range 2 to 3. Which is quite an amazing design. Like this is what the state of the art is. Like most of the distributed systems, when they put data in different nodes, they use consistent hashing, and this is the most stable form of hashing, right? So I usually try to test people if they know consistent hashing, and if they don't know it, that's okay. I mean, I don't like to penalize them because it's a more advanced data structure, but I at least expect them to come with alphabetic and random and discuss the pros and cons, right? As like
But
you said that.
Ravi,
Go ahead.
even consistent hashing will have the same problem as random hashing from prefix perspective, right? Like prefix के लिए
Correct.
आप कैसे करोगे? Unless you put prefix in all the nodes
Correct.
which fall in that hash.
Right. It's a form. So consistent hashing is from the family of the random hash functions. So you're correct. So उसकी property hold
Okay.
करेगी, that prefix
Okay.
will be tricky. Okay. So let's move
Ravi,
into.
can you go back to the previous slide? हाँ, तो इसमें जब जैसे वेब सर्वर 3 डाउन हुआ, तो जो हमें कैसे पता चलेगा कि कौन से स्ट्रिंग्स इसके साथ डाउन हुए, मतलब वो मैपिंग कहाँ पे स्टोर होगी?
So typically, like the way you kind of do it is, that's a high level wala architecture तो अभी नहीं आया, but the way you do it is you will have in a high level architecture, right, of it, you will have a metadata server.
ओके, अच्छा, तो जो रिवर्स मैपिंग स्टोर करेगा एक तरह से।
हाँ, वो बेसिकली जो हैश टेबल होगी वो स्टोर कर लेगा, एंड देन
अच्छा,
आपके नोड्स होंगे, राइट। तो ये एक माइक्रो सर्विस हो गई, राइट। यू कैन से ये लाइक ये नोड 1 हो गया तो माइक्रो सर्विस हो गई, दिस इज नोड 2 एंड अप टू नोड लाइक 46, जो भी 14 नोड्स हैं और वो सब अपनी इंडिपेंडेंट माइक्रो सर्विसेज हैं, एंड इसको लाइक दिस मेटाडेटा सर्वर नोज कि which keys map to which, right?
But Ravi, अगर आप redundancy कर रहे हो on the next server in the ring, then you don't need the metadata server, right? Or do you still need it? Like, can you go back to the old slide? Agar, let's say Dubai is in 2 and 3, right? But if you do Dubai in 2 and 3 and also do redundancy of Dubai on 4 and on 5, then if 2 and 3 goes down, automatically it will get to 4, right?
But how do you know which range Dubai falls into, right? So the function, which is the function which is the hash function, metadata server knows it. You can imagine like that. So pretty much like if you imagine what the lookup path is going to look like, so what will happen is that you would have Dubai, and then there's a function that sits in the metadata server, which basically says function on Dubai is range 2 to 3, right? Which is range 2 to 3. So this information lives in the metadata server. And so you basically need to have a metadata server. Otherwise, like how would you figure out which range does the this thing fall into, like Dubai fall into which range, right? Does that answer your question? I got a bit confused. Sorry for that. I think.
Yeah, it does answer the question. And what if the server comes back up? Will we rehash it again?
Yes, you rehash it again. Because the disadvantage of keeping more strings on one server, as we said, right, that it may not be able to handle the QPS. So then you have to like further rehash. So instead of that, when a server comes back, you just kind of move to the stable state.
Okay.
Hey Ravi. So if we, let's say, we start getting more strings, like there's a case where we start getting more strings, and our existing number of servers aren't that sufficient because we are not meeting the requirements now. So we need to start rehashing every time that we get more strings, because this is so this particular problem is for strings, right? But think about, let's say, documents, right? We keep getting more and more and more documents, right? So how do we then tackle this problem?
No, you're correct. I mean, that's a good question, and there is no one single answer, right? There can be different approaches to tackling it, right? So initially, what you will end up kind of doing is, what you would end up doing is you'd first try to saturate, right? So you would try to saturate the 40 web servers with, say, whatever is like a 10 terabyte of memory, or like the 100 billion strings, right? Now, once that is done, once you've hit the saturation level, then you would basically, what you would end up doing in, I think, in consistent hashing, as I kind of think about it, because I haven't completely thought through it, but what you could do is that in consistent hashing, you can introduce servers in between as well. I think that's what I remember, but I have to go back and read the paper. So if let's say, let's just think from first principles, right? If you introduce a server in between, then only what you need to do is that it's basically imagining that this web server went down and then came back up. So the keys in this range will have to move, right? Pretty much the keys in this range will have to move, right? No, actually, sorry for that. I think, yeah. So I was correct in the sense the keys in this range. So let's say this is web server n, this is n minus 1 and n minus 2, right? So pretty much in these two web servers, the keys will have to match. So consistent hashing keeps things very, very stable, right? But if let's say you're going with alphabetic sorting, or if you're going with random hash, then you might have to rehash a lot of strings, right? In random hash for sure, you might have to rehash all. In alphabetic sorting as well, you might have to rehash some subset, but you will have to do that, because if your each of the web servers is saturated by memory or by CPU, then you introduce more like web servers, right? And then you have to rehash some ranges, and that depends on the hashing function, right? So consistent hashing there also does, I think, better. That's what I can, yeah, imagine.
So we have a question here. So when we are talking about the storage, right? Consistent hashing, random and alphabetical way, right? So we are trying to divide try into multiple web servers. Let's say 40.
Correct. Right.
Right. So I've just sent a link on Google Chat. Uh, if you can open that, I have a question so that will be easy for me to ask. For example, if this tree is on the high level, it has A, right? On the very high level, it has A, and then you have N, and then you have L, whatever, right? For example, one web server is trying to keep the data for A, just A, right? The hashing or whatever consistent hashing, right? But let's say you have to, because its memory or disk got exhausted, right? Because 256, more than 256 gig, right? Now you have to divide and take some substrings of A to some other servers. How does that work?
Correct. And what scheme are you using? You're using the alphabetic scheme?
Yeah, alphabetic or consistent hashing. I'm having some hard time to understand exactly that.
So दोनों में answers different आ जाएंगे, फिर that's where it will
Sure.
be. So जैसे कि in alphabetic hashing, what you could do is like what we started off was saying that you put all A's into web server 1, right? So what you can also do is you can basically say that instead of doing that, you basically have another layer. So all A, so any string, so imagine that all strings that start with A, right, is a range R. So you basically divide the range into two parts, right? So there is range 1, range 2, and maybe the way you divide it is in all the strings that start with A and the second letter is M, so that is range 1, and the range 2 is all the strings that start MN to AZ, right? So A to AM. So like you can basically do just a secondary functions होते हैं ना hash में, so you can basically have a secondary function which basically says that so that's one way. It's basically a technique. You can come up with many techniques. This is not the only technique. In consistent hashing, the advantage that you get, I think, is if let's say one of the web servers starts to get filled up, right? So in this range W0 to W1, if W1 starts to get filled up, you can introduce a server in between, right? And then what will happen is half of the strings will go in W1 and half of the strings will go in W0.5, right? So more naturally, it basically stabilizes the system, but the approaches will be different, right? So like half of the try will go in. Go ahead.
Yeah. So I was saying that the high level node becomes AN or AM or AZ or something like that, right? It doesn't stay A.
It doesn't stay A.
Okay.
Like you can also like imagine that like the real world system will not be as simple. Like it will not be that A एक में जा रहा है, B दूसरे में जा रहा है. It will be very complex. But there's a way to understand, right? And this is also a question that the interviewer can ask, right? What if A like hotkeys वाला जो problem होता है वो है, that's how you try to answer it. If R is there and R has like 10 like billion strings R में है, they will not fit into a server. Then how do you go about it? So then you basically say that you have a secondary hash. Okay. I think guys might run out of time as well, so feel free to like leave in between. I'll share the video anyways, and not feel bad about that. Okay. So and then availability we didn't discuss, right? So availability, as like somebody did point out, so I don't remember names, sorry for that. Really bad at that. So in terms of availability, there are two approaches to availability in memory, and the most common one which is used is that you basically have redundancy, right? So if you go and read like how distributed file systems work, is usually have redundant storage in secondary servers, right? So basically, the idea is that you would have Dubai sits in web server 1, but it'll also sit in web server 2 and 3, right? So you have a replication of 3. The disadvantage is that you will basically end up using a lot of memory. So costs will go up, but your availability will be high, right? So that's like the primary mechanism. But there's an alternative as well, which is usually not used. But what you can also do is, as I kind of discussed, was that let's say this is in memory, and you basically serialize the try on disk, right? And this is just an exploration, so you don't have to like know it, or it's just thinking from first principles that when your web server goes down, right, what you could do is that you could have a on disk representation of the try, right? And this, maybe you can just keep it as a hash table, right? So you probably don't even need uh, to to basically store it as a try, right? And you can do lookups just from the disk itself, right? So what will happen is that although your system will remain available, it will run really slow, right? And it may also happen that prefixes might be a little hard, because on hash table, like, prefixes are hard. But uh, the advantage is that you could ensure that the system remains up and running, right? So that's something that you can discuss with the interviewer, that like if you don't want to keep redundancy, then you can also keep it on disk, right? And then on disk there are more complications, so you can either serialize or deserialize. That's option one. And the other option is you can write it as a hash table and then look up on the hash table the way you do it on databases, right? So those are two different options, right? uh, both of the options are suboptimal to the way redundancy is done in memory. So usually the right answer is to keep it in memory, have redundancy, use more memory. That's fine, because we said there's infinite memory. But if you have to discuss, you can also discuss approach one, which is serialize. Go ahead.
हो जाएगा 10 मिनट
Sorry. Approach one, and then approach two is keep a hash table on disk. Right. And the on disk approaches will not really work well, but like something to discuss, right? Okay. I'll quickly, yeah, discuss. So one thing that I didn't discuss, what the high level uh, diagram tends to be, right? And then what other things were there?
Hey Ravi, I'm in this.
Go ahead.
So can you all focus on what if we want to deploy this our design across different continents, or let's say different regions, let's say for USA, for India? How will we scale out the HLD that we are discussing?
So if you have to deploy it across, so usually the way you kind of deploy it across regions, let's say you have region 1, have region 2, right? And I think that I'm also thinking from first principles, right? So there are different approaches to go about it, right? So one is that you can keep redundancy across all the regions, right? So you can have copies of, so you have a try, right? And you can just keep a copy of the
So I think there's a more practical problem that the search result, let's say that will show up in your search, autocomplete search will vary across regions. So from that perspective, do you think that these companies that are building this, do they have completely different data set for, let's say, India, US? Does it happen like this internally? Because that will impact the search result. Yeah, I can definitely, let's say, sync data across different regions. That is very easy nowadays. But going to more internal problems there, are they creating different set of data set? In that sense, are they just saving the entire data set for India is completely different. But other problem that will arise from there is, as an Indian, if I'm searching something, I will also get US results. So are these the same data set, or they are querying across various regions as well?
Hmm, hmm, hmm. So let's think of what the application is. So if the application is Google, you might want to have 80% overlap in the search results. So somebody searching, if I as a user am searching from India or US, my search results should not be very different because it's personalized to me instead of where I am. It can be like 20% of it can be different for sure because the region does play a role, right? But if the application is where you have let's imagine a different application, right? So maybe it's a travel app, right? And in a travel application, maybe region plays a lot more importance when you're like figuring out which city to go from to which city, and it basically prioritizes local, or maybe it's news, right? So it prioritizes local news. So autocomplete for local news may be very highly prioritized. So then in different applications you would end up having different types of representations, right? So in, I think what Google would end up doing is that it would have a model which is eventually consistent, right? So uh, any data that is like being indexed in region 1, like that comes from region 1. So if like there's a website you've created in US, then like region 1 is US, right? Let's say region 2 is in India, then for sure it will get indexed in region first, region 1 first, which is in US, because the website has to be available for search in like index in region first one first, and then maybe it takes like a few hours for it to get consistent with region 2, because you basically want that website to be available everywhere, right? And have results there, right? Now if the, so, and this brings in a lot of complexity, because how much time does it take? The eventual consistency model protocol has to be correctly implemented, right? Those complexities will be there. But the advantage that you get is that you basically have consistent results eventually, right? The second model is that, which is a more like a loser model, which is that if a website is in India, like is created in India, and you really don't want to it to be represented in US for a long time, then you can basically shard, and you can say that uh, that India ka data remains in India and US ka data remains in India. There's no like the tries are not even shared and data is not even shared, right? So that's a loser model. And the most strict model would be that you don't even allow searches on it unless it's synced across. So typically, like if you have a, like for example, a transactional system, right? So let's say banking system, you created an account and you want that account to be available in all the regions, right? So what you do is you have strict consistency, and so data has to be available across before it gets right. So the way I kind of would think about is firstly figure out what the app consistency model is. So they can be strict, they could be eventual, and then there is very, very loose model, right? And the loose model, uh, like in eventual, like you may have a sync, which is a few hours of sync, right? This is like this may be in minutes, right? And here, like the tries have to remain in sync, right? But here, like in the loose model, that like the tries may be like they might just be distributed, and you might not even want to keep them in sync, right? So the tries maybe just sharded, and like data just remains for one region, data remains in one region, and for the other region, data remains in the other, and they may not even share it. It could happen, right? But yeah, I would love to hear what your thoughts are. Like, do you think this makes sense, or have you seen better better designs you've kind of worked through?
No, I practically did not get a very good answer for this. But in the loose model, I think there will be a constraint that because it is not pure data, right? And a try, if I'm deploying a try, it's definitely going to be immutable on my production system. Because if I keep adding something, then definitely my performance will take a hit. So it
Correct.
would be that across region, we would try to sync up once and maybe recreate the entire try. And post that, obviously, we'll serialize it and save it somewhere for, let's say, a different copy. If I want to bring up another node, it should have the same image essentially. So yes, I think that would work. Uh, it has to be eventually considered. There might be some logic based on which we have to decide whether I want to give result only from one region or another region, or maybe they might be querying across both the region and merging it. I think it is very common as well for multiple companies, like in infrastructure as well, to query across different regions and then have a different algorithm which actually decides based on my preference, as you mentioned, location preference, my whole search history, like what result should be shown to this user. It's possible that they might be querying across two regions as well.
Correct. I
Every
agree.
time.
Yeah, I agree. I mean, it might be possible that you end up querying across two regions, right? Because just the latency of updating the tries may be high because they're immutable. That I completely agree. And then when you kind of query across two regions, then the disadvantage would be that like queries would run slower. But maybe you're okay with that, right? Um, yeah, I think
Yeah,
what
and
I'll do is,
yeah,
huh,
yeah.
go ahead.
Sorry. So, how do you think in this design should you factor in the real-time updates? Because tries are not actually best suited for that. Or maybe we can do it, swiping out tries every time. Let's say uh, I'm coming from a point of view that if I want to show up, let's say IPL search results, right? Because that also comes up immediately, or some major news. So how are these companies handling this? Should we have some hybrid model, like maybe say for standard search we have tries, for real time data we have some other handling?
Hmm. Right. So this, like the problem that I kind of was discussing was not designed for very kind of real-time updates because tries will take time. So if you have to rebuild the whole 1 billion, like, so that definitely is true, right? The way I could think about is this problem is you could, yeah, like ideally you would want to have two different, like I could come up with two approaches. So one approach that I kind of think intuitively works is that you have a larger try, right? Which is, let's say, V1, and then you have a smaller try data structure, which is version V2, and then eventually you create a version V3, which is a combination of it, right? And the way you kind of keep it is when you are getting updates, you basically buffer those updates, right? And maybe at every 5-minute interval, you basically persist them into a smaller try, right? So this is more real time and this is a little bit stale. And what you do is when you do a lookup, you basically merge the results back, right? So you basically have results from R1, R2, and you merge them. And this buffer. So pretty much the approaches would converge, as you're saying. You have a data structure which is like a buffer. So the buffer can be a small hash table, right? And you can just do very unoptimal lookups on that because it's a small structure. Like 5 minutes में कितनी updates आएंगी, right? And then you can push it into a smaller try. And then at R latency of an hour, you basically merge those tries, right? And this is not the only approach. You can come up with like many different approaches, but the intuition can be, which you already answered in your question, which is that you have two different data structures. One is optimized for fast updates, one is optimized for slow, like fast lookups, and then you kind of use them together, right? And here also, I think maybe you don't even need a smaller try. You can just keep maybe a hash table, or you can keep a tree because that will not impact your performance that much. It's just a small data structure, right? So that's how I would think, yeah, you would go about it.
Got it. Thanks.
There was one more question I think Rohan had asked, a couple of more. So one was, so there will be meta node servers having trial event segments, active servers which have those strings meta. So yes. So eventually, like in the high level diagram, there will be a meta server, like the metadata server, which is usually called, which basically knows that which nodes do the different strings fall into, and then the nodes themselves know within the try where that string remains, right? So that is how like the simplest kind of design can be. Now you could have multi-level like node servers as well, but I think that would probably become way too complex, right? so you have one high level server, and then the individual workers or individual nodes pretty much know where in the trie the data remains, right? So that's how like the design could be built, right? And then you also talked about LSMs, so merging two trees. Data structures do have versioning concept, and then so I haven't like thought from the perspective of LSM tree, although you are right in the sense that merging becomes easy. Now, like you would have to ensure that you are able to keep levels within tries. Like I don't have a very good control over the idea of how do you kind of keep build with LSM, but you could, right? Because I do agree with the fact that if you're able to like design a data structure that merges and updates very quickly, then it might become easier. But there are more complexities as well, right? So, like in tries, one of the other complexity is that when you're building this data structure, you also have to account for popularity of strings, because let's say when you type in S, right? So with S, right, what Google would tend to do is it will basically pull out results which are the most popular results. So we didn't go into what the object structures would be, but you would also keep a number with each object, which is how popular that is. So when you merge, can you merge them in a way where the popularity gets updated? Now, as I think about it, maybe that is also possible, but I really don't have a good answer to like, would it be better if you just use LSMs than a basic time? It may be, but yeah, not don't have a very good answer to it. Yeah.
Okay, Rohan, are you pointing to using LSM the way Cassandra does it? Like save everything to commit log and then create SS table eventually and do a lookup?
It did seem like, I don't know if Rohan is listening, but it seemed like he was pointing to keeping it persistent on disk. That's the only thing
That's
is
the
that
way.
like, go ahead.
I don't know. I think it's an interesting take. I'll definitely go and explore this part.
Okay. Okay. So makes sense. Yeah, at least I haven't understood well, like as to how like uh, the persistent data is persistent, like say Cassandra, how do they merge? Like I haven't looked at those algorithms, so maybe there's a better time. The only thing is that like within this constrained problem, I think like keeping it on disk would be a problem. So you have to keep things in memory. Maybe there's an efficient representation in memory, and then the try may be just a very simplified structure. In actual, like the structures may be more complex. That may happen. That may probably be the case, right? Which I agree. I think that makes sense. So I'll just try to. There's one, like I'll just try to do one last thing. I think that might be helpful. Is just give a very high level diagram as to how pretty much tends to happen, right? So in just terms of the high level diagram, right, you usually would have a client, right? And this, I think you might have already kind of gotten to, you usually have a load balancer that sits, right? You tend to have typical metadata service, right, which basically know where to look for the strings. Right, and then each of the metadata servers has access to all the like independent node servers. So they may not be W1 to W4, and then they have access to the storage. Storage can be like an S3, it could be, and as others said, like if you're kind of trying to store it in LSMs, hash table, like that would be pretty much on disk. Right. So typically, like on a very high level, you would end up having at least these components, right? And you can make it more complex. Like you can always have like an API gateway in between. You can have like multiple levels of web servers, and with metadata web server, you can have like there could be a cache that sits in between the web server and the like these nodes as well, where the try is, right? That could also happen. But typically, like the most important components are these, right? And like the way I kind of ran through this problem was from the design perspective of an interview, right? So thereby, I definitely glanced over a lot of smaller, like lot of things that we can kind of double click on. But like typically, those would be some of the elements that you should discuss with like should be discussed, right? Okay. So yeah, I mean, yeah, you can have Zookeeper. Uh, uh, the only thing is that can you keep a lot of uh, custom business logic in Zookeeper? I don't know how well. It's good for coordination for sure, so that makes sense. Uh, but in like in actual, at least from what the system that I've worked on, the metadata server also keeps a lot of information, which is like uh, definitely hash you can store in Zookeeper, but you also need to coordinate other things. For example, when a worker goes down, how do you rebring that up? How do you redistribute? So all of that business logic also needs to remain in a metadata server. If it's possible to keep it in Zookeeper, then you can definitely keep it. But I've seen usually the metadata server using a Zookeeper and then keeping a lot more business, like a wrapper over Zookeeper, and then keeping more business logic in it. But that's fine. I think that's kind of up to the design. Yeah. I mean, you guys can discuss. Like everyone can also learn. Like if you think LFM is better structure, feel free. I would love to learn as well, for sure. Yeah. So I think that was uh, mostly what I kind of wanted to cover from this, right? There are a few aspects to it which I didn't cover, which is like if you had to like design a simplified API between the front end and the client and like the web server, which is the lookup server, right? How do you kind of define the API? So that's one part of it. The other couple of things that also could be thought through is instead of just doing a prefix search, if you had to do like approximate search and a suffix search, how would you do that? So that's something that's just like a mind exercise that could be done. And definitely doing this persistent on disk, right? Those are three questions that I had in mind that could be good to kind of think through as to how would you go and design it. Yeah, I think that's like pretty much it. I would love to kind of, if you guys have any feedback, anything that you want to ask, would be happy to answer those, or like we can discuss. I don't know if it was useful for you guys. I was just doing some experiment, trying to see if it brings some useful knowledge to you guys. Yeah. Okay. I think what I'll do is I'll share the like the video. And there are a couple of questions that I think I'll just read on, which is one was this LSM thing and the other was the geo replication thing. And otherwise, thank you. Thank you for taking the time out. Take care, guys.
Ravi, we have just one more minute.
Go ahead, go ahead, go ahead.
Ravi, Jibin here. So one thing what I want to ask was like, what are the kind of telemetry things you will have for these services? Like usually I've heard like for interviews it's good to mention about telemetry.
Correct, correct, correct. So typically, like metrics, there are some standard set of metrics, right? That you end up having. So like one, and you can go through. So one is that API, like you would try to keep a good control over API. So API latencies, availability, that is just a common set of metrics that you would tend to have. In actual operational settings, the non-intuitive things that I thought were useful was how do you debug the try, right? So whatever data structure, let's say you're using LSM, you're using a tree stable. Uh, so Abhimanyu, if you can just wait, I'll try to answer that like after this, uh, right, and give some resources. So how do you debug the try? That was interesting because we ran into some problems. I thought about it. How much memory is the try using? How much memory is each node of the try using? So that was interesting, which is non-intuitive, a bit non-intuitive. Then the other set of things, so API I kind of did cover. Then the other side of things you kind of try to look for is um, you could look at like, for example, system properties. So disk usage, memory usage, network usage. So that's also pretty standard. Um, the other set of things in search that tends to be very useful is you look at relevance, which is a little bit something we didn't cover, which is that in relevance you try to look for MRRs. MRRs like mean reciprocal rank. So which suggestions is the user clicking on? Are the suggestions relevant or not? And that's something that like people do also look at, which is very important for search. So yeah, like you divide into some buckets. So there would be API, which is business logic. You would try to look at system constraints. You try to look at maybe some very deep dive data structures, which is like the try is the core of it. And then last is you look at relevance, which is like pretty much like how good is your search engine and the ranking performing, right? So I think those would be 4 buckets, and then you can like enumerate metrics in it.
Got it. Thanks, Ravi.
Okay. So when you like, I think in my like journey, like or how I've kind of learned system design is I've done a few things. So one is that like to learn anything, you have to build something, right? So one is like if you are building a system, then you quickly learn aspects of it, right? So you basically pick a project. A lot of people do ask me, and I've discussed this with a lot of people as well. So one way is either the place where you're working at has a good problem that you can take up and you build a system on it. If that is not the case, then there are open source projects on Apache, which I really like. There, like you can like take a look at some of the projects. Like Spark is a project on which like Databricks as a company is built. There's Kafka, and these are open source. You can go and fix bugs there, and you can start to them. Yeah, I can definitely point on Apache. Okay, so I'll do that. Maybe I'll just do it in the email I sent, right? So that's another way, which is that open source projects try to contribute to them, and you can get started. They have very good mailing lists, very open, like they're very open set of people who would end up asking you to get. So that's one. So you have to build something for sure, and to learn, I think there are good courses. So there's like courses that are available on Coursera, on Open MIT Courseware, YouTube. Just don't go with any course, but try to see if that course is really good. I think I've learned a lot of things from Coursera and some good lectures on YouTube. So that's one. Another. And then if you are a book leader, then there are a couple of books that I can definitely suggest, which is like there's designing data intensive applications, and then there is a couple of more books on system design, which can be a good starting point to kind of go and read. That's third. And then I've seen some cohort-based courses also get started in the last few years. So I think in India, like Arpit is one who I know he runs a cohort-based course. It's a little expensive, but it's pretty good. Like I've seen the contents and his knowledge is pretty good. So it's much more structured, like something like this, but more structured, and you will have slides and everything is prepared. This was a little informal, unstructured, but that's another way, right? So yeah, I'll point to resources in an email I'll send. But the idea is build something for sure. If you don't build, then there's no point of learning. Like theoretical knowledge will not help. But with that, you can like either do a book cohort or you can do an open course on web, and then that should be sufficient to get started. At least that's how I have learned it myself. Yeah. I mean, if you guys have any other ideas, feel free to point them as well. Good. Okay. I think sometimes it becomes very a monologue. I don't want to do that, but like it's very hard to avoid it. Okay, I think I'll wrap it up then. Cool. Thanks, guys, for taking the time out. It's probably getting late. Good night.
Okay, thank you so much, Ravi.